So let's get started. So this is our work, lightweight cache replacement management for instruction-heavy workloads. So this work was done at A&M by all these authors. Unfortunately, a lot of them couldn't be here because of visa issues, but I'm going to be presenting on all our behalfs. Right, so let's get started. So first, let's talk about what is LLC and why do we even care about it, right? So LLC provides the last opportunity to access the data before paying the cost of high memory latency. So as all of us probably already know, that the memory speeds are not progressing as fast as the core speeds are progressing. So we want to make sure that most of the requests that we make from the memory actually hit in the caches so that we don't really have to pay that high memory access latency. So caches are one way to achieve this. So effectively just like a Cliff's Note version of what caches are just, they just hold a copy of the data which is in the memory. And if it just so happens that the core requests the same data which the cache holds, then you don't need to go to the memory. So the last level cache is the last level of this cache hierarchy. At the bottom, we have the level 1, level 2, and then we have the last level cache or the L3 cache. Moreover, we find that increasing working sets, as found by Kanev et al. In 2015, of applications are putting growing pressure on LLC. Because these caches are actually pretty small compared to the main DRAM, what happens is that you cannot really store all the data in these caches. So some of it is going to spill over. And what we have found, not we, but like these authors have found, is that with modern applications, the spillover happens quite frequently because the working sets just don't fit in the caches anymore. Moreover, we find that due to the huge gap between the memory and the processor frequency, as I mentioned before, a miss in the LLC can lead to significant delays. So if I miss, say, in the LLC, I have to go all the way to the memory and get the data back, which is a costly affair. So we want to avoid that as much as we can. So how can we do that? Well, the answer to this question is replacement policy. So replacement policy is the policy which manages the data in the cache. So in the cache, we need to decide what to keep and what to throw out. And the answer to this question is given to us by the replacement policy. In this work, we are focusing on the replacement policy of the last level cache, which is the largest among all the caches in the cache hierarchy. And yeah, so let's see how we can design like an efficient replacement policy. And it's important to note what exactly we mean by a good replacement policy. So a good replacement policy aims to retain useful data by throwing out data which would not be used. So we want to keep only the data that we're actually going to use in the cache. So now let's talk about why is it that we chose to work on instruction-heavy workloads for this work. Well, the reason was that we found that instruction-heavy workloads increasingly have really, really large instruction footprints. The problem with large instruction footprints is that they don't really fit in the L1I cache. Since they don't fit in the L1I cache, the data is going to spill over from the L1I cache to the L2 cache to the L3 cache and so on and so forth. So we need to figure out how to deal with these large instruction-heavy workloads. And that's why we have proposed this policy. So let's see. So we find that instruction-heavy workloads show less temporal locality outside of loop. So typically what happens is that if suppose I have a load instruction, if that load instruction is being accessed in a loop, you will have a lot of temporal locality with it because I access data A, I'm going to access data A again in the future and so on and so forth. But with instructions, once you access an instruction, you just execute it and that's about it. Unless that instruction happens to be in the loops, you're not going to have a whole lot of temporal locality. Furthermore, we find that all the replacement policies, which were, well, not all, at least all that I am aware of, the replacement policies which have been proposed so far often use PC-based indexing. So PC is your program counter. And the problem with PC-based indexing is that if you don't really have the PC, you cannot really use it. So suppose I am, say, some company, pick your favorite company, and I buy a core from ARM. Now, if ARM doesn't export its PC, I really cannot use these older policies because I just cannot connect it to the core. So we want to have a policy which doesn't really rely on PC-based indexing and which can also provide high performance. So let's talk about some related work. I'll go over this fairly quickly. I'm sure the authors of these works are here somewhere in the audience or I'll discuss. You can talk to them if you want more details. So let's get started with RRIP. So RRIP is re-reference interval prediction. And so the key idea of RRIP is that instead of classifying all the cache lines into fine-grained granularities, we classify the cache lines into broader granularities. So let's take an example. So let's say we have a 16-way set-associative cache. Now in a 16-way set-associative cache, with an LRU-like policy, you're going to classify each cache line into one of 16 categories, all the way from MRU to LRU. So what RRIP paper said was, instead of doing this fine-grained categorization, if we use broader categorization with just 4 classes, we can actually get better performance at lower hardware overhead. So that's what this RRIP paper is. So they propose something called RRPVs, which are re-reference prediction values, which are the 4 categories that the paper proposed. Then Khan et al. Proposed sampling deadlock prediction. So my advisor also worked on this. Is somewhere in the audience, somewhere. So it predicts it tries to predict which cache lines are likely to be dead in the LLC. So a dead cache line is a cache line which you just access once and that's it. So if you just access that cache line once, there is no point to really hold it in the LLC to begin with. So this work tries to predict which cache lines are going to be dead and which are not going to be dead. Then we have SHIP. So SHIP is another kind of a predictor which decides at which RRPV am I going to insert an incoming cache line. So that's an improvement over RRIP. And then Jimenez and Teran, Jimenez is my advisor. Jimenez and Teran also proposed multi-perspective reuse prediction, which improves upon the prior prediction-based replacement policies by using perceptrons and by taking various information into account before making a decision as to where we want to place the incoming cache line. And then finally, we have Mockingjay, which represents the state-of-the-art replacement policies. The key idea behind Mockingjay is that it tries to mimic Beledi's replacement policy. So for those who might not know what Beledi's replacement policy is, this is like the provably optimal replacement policy. You might also know it by clairvoyant replacement policy for OS folks and stuff. So it goes by a lot of names. It's really famous. But the problem with Beledi is that it requires you need to know the future because otherwise you cannot implement it. So it's like a theoretical maximum, not something which could be practically implemented. So now let's talk about some limitations of prior work that we are trying to fix in our work. So LRU-based policies such as RRIP, so those policies make the assumption that the recent past is a good indicator of the near future. So what that means is that if I just use this cache line, I'm likely to use it again. If I use this cache line maybe 10 cycles back, I'm less likely to use it in the future, and so on and so forth. This effectively just mirrors the past into the future. The problem with this is that while this works for the level 1 and level 2 caches, at LLCs, the access patterns are often sporadic. Why? Because the L1 and L2 are going to filter a whole lot of accesses. And since the access patterns are sporadic, this assumption doesn't really hold. As a result, you don't really get a whole bunch of performance from LRU-based policies. Moreover, policies such as SHIP and Mockingjay require significant design effort because, as I alluded to earlier, if your policy requires the PC, you need to have the PC in the first place. Moreover, if the policy has complicated logic built into it, that's also significantly increases the verification effort that engineers have to go through to implement that stuff. And then finally, we find that policies that don't take prefetching into account as a first order metric perform worse. So what do I mean by prefetching into account? So at a cache, you can get 2 kinds of requests. You can get a demand request or you can get a prefetching request. So policies that just treat everything as exactly the same often end up performing worse. Why is it not good to treat everything as the same? Because prefetching is a speculation, right? You're prefetching that I'm going to use this sometime in the future. I don't know when, or I don't know if I'll use it, but it's a prediction. But demands are less demands are also speculative, but less speculative than prefetches. So it's important to consider both of them as separate classes. And that's exactly what we do in our policy. So what is it that we are proposing? So we are proposing a replacement policy which gives us the best of both worlds, which is we want high performance at low implementation cost. So now let's talk about what are IPVs. So our policy is called PAC IPV, and the IPV of PAC IPV stands for Insertion Promotion Vector. These were proposed by Jimenez in 2013. And this is a vector which concisely represents the promotion and the insertion policy for a particular cache. So we have an example of an IPV over here. I will go through this. So just to give you a little overview of what you're looking at. So in our work, we are using RRPV. So the same thing which was proposed by an RRIP. So RRPV is from 0 to 3, so 0, 1, 2, 3, instead of using LRU positions as were proposed by Jimenez in 2013. Okay. And since we are using 4 distinct RRPVs because 0, 1, 2, 3, our IPVs are 5 elements long. Why 5 elements long? Because the first 4, these first 4 elements in yellow, or the first 4 numbers, those represent the promotion policy, and the last element, this one in magenta, purple, whatever it's called, represents the insertion policy. So let's see how this works. So let's say we have an example of a cache set over here. We have 6 cache lines, A, B, C, D, E, and F, and we have this IPV which we will use to manage this cache. Just how to read this diagram. So the first alphabet is the name of the cache line, and then the next element is the current RRPV position. So we can see that A is at position 0, B is at position 0, and so on and so forth, right? And and if you all are not aware of RRIP, typically the way it works is that the lower numbers are the more recent positions. So you're not going to evict them as earlier as compared to higher numbers, okay? So right now, as it stands, the cache line C at way 2 is going to be evicted first. Okay, cool. Let's see. So now we get a demand for cache line D. So first of all, we see that we already have cache line D. So that's a good start, right? We have this line over here, so we can service this cache line. However, we see that since we get a hit on this cache line, we need to update the replacement position of this cache line, or the RRP of this cache line. And let's see how we do that. So we look at the current position, which is 2, this is 2, and we index this IPv with this value 2. So we go to 0, 1, 2. At position 2, we find that the value is 1. So we're going to update the current RRPV of cache line D with 1. And that's exactly what happens. Now let's see what happens when we get a fill. So whenever we get a fill, we need to first of all decide who do we kick out. So as with RIP, we just pick the cache line with the maximum possible RRPV. In our case, this happens to be cache line C, so we kick out cache line C. Note that it might be possible that there are no cache lines with the maximum possible RRPV, in which case we age every cache line by 1 and try again. Or there might be multiple cache lines with the highest RRPV, in which case we just randomly pick one of them and kick it out. So we evict C and we insert the incoming cache line G, and the incoming cache line is inserted at position 2 because that's what's represented over here. So this thing is basically what we have over here. So that was what IPVs were. So now let's talk about what are PAC IPVs. So PAC IPVs they stand for prefetch aware coarse grain IPVs. So prefetch aware is because we are specifically considering prefetch. Coarse grain because we are using RRPV positions instead of using LRU positions, and IPVs, as I explained to you before. So they extend the idea of IPVs to incorporate prefetch as well. So a PAC IPV pair consists of 2 IPVs. We have the demand IPV and we have the prefetch IPV. So all the demand requests, the inserts and the promotes, are going to be handled by the demand IPV, and the prefetch requests, the inserts and promotes, are going to be handled by the prefetch IPV. So just to make sure that we all get this idea, let's go over an example. So we again have 2 IPVs, a demand IPV and a prefetch IPV. We get a prefetch request for G. Since it's a prefetch request, we look at the prefetch IPV, and we look at the cache to see which position G is currently at. So G is at position 2. So we look into the prefetch IPV, look at the second index of 0, 1, 2, and we see that G must be promoted to position 1. And that's exactly what happens. So just to recap, what is it that we are proposing? What's new about our work? So first of all, we are proposing to use RRPVs instead of LRU positions as proposed by RRIP. So this helps in two ways. First of all, it reduces the overhead of this policy, and secondly, it also helps to cut down the search space, because up till now, I just showed you how IPVs work. I never told you how do we find these IPVs in the first place, right? So we're going to have a search algorithm which finds it. So we want to make sure that the search space isn't too large, because otherwise you cannot finish your search. By using RRPVs instead of LRU positions, our IPVs can be shorter, and that's why we can actually exhaustively search the whole space. Furthermore, we also introduce distinct IPVs for prefetches and demands, and that leads us to invent PAC IPVs, which is a simple policy for high-performance cache replacement. So first of all, let's see what's the benefit of having separate prefetch IPVs and separate demand IPVs. So over here, you see this is our LRU, so this is our baseline, so that's why it's always at 0. And then we have something called PAC IPV distinct. So PAC IPV distinct treats prefetches and demands as distinct requests. That's why the word distinct is there. So it has a distinct IPV for prefetches and for demands. PAC IPV identical, as you can probably guess, has the same identical IPV for demands and prefetches. And we see that PAC IPV distinct outperforms PAC IPV identical. And this is the proof of our hypothesis that having separate IPVs for prefetches actually helps. So how do we go about finding the IPVs that we're going to use in our policy? So first of all, we divide a program into the training and testing phase. So this is close to how you would do machine learning stuff. With just 4 IPVs, we find that the IPV space can be searched exhaustively. And we further narrow down the space of all IPVs down to just 4032 pairs by using some obvious heuristics. And then we finally evaluate on the testing set. So now let's see how our policy performs. Or rather, let's see how the workloads, so what workloads we are using. So we are using CVP workloads. Why do we use CVP workloads? Because we wanted to focus on instruction-heavy workloads. So that's why we chose CVP. We divide them into the training set and the testing set. We further filter them based on the L1I MPK so that we only get the instruction-heavy workloads in these two sets, the training and the testing set. With that thing said, now let's look at the simulation infrastructure. We are using ChamSim for our work, and this ChamSim has FDIP integrated into it. So if any of you were curious about that, and also we have configured ChamSim to mimic Alder Lake processes from Intel. So now let's look at some training results. Again, note that we are training for this particular graph, we are testing on the same set at which we trained. So like this is just to give you like a high level overview of like what we're gonna expect. So we can see that as usual, LRU is at 0 because that's our baseline. The pack IPv, this orange line, is the line in which we are picking the best IPv for each workload. So I have 10 workloads, I get 10 different IPvs for each and every workload. And if we were to pick the best IPv across the whole workload suite, which means I have 10 workloads, I pick just one IPv which performs best across all of them. That's the pack IPv line. This is the blue line. So this orange line is kind of a limit study. The blue line is actually what we are implementing. So we pick the best IPv across the whole suite, and that's the performance that we get on the training set. But that's not that interesting because, yeah, of course, you train and test on the same thing and you get this high performance. That's not surprising. So let's see how it works on testing set. So on the testing set, we see that we are able to match the performance of Mockingjay, and we are able to outperform both strip, drip, and ship. Note that pack IPVs are really, really simple compared to Mockingjay. And even then, we are able to match the performance of Mockingjay while outperforming strip, drip, and ship. Let's look at the hardware overheads. So here we can see that the hardware overheads of pack IPv and drip is exactly the same. It's 12 kilobytes per core. So as I said, like the policy that we are what we are proposing is really, really simple. I mean, honestly, it's just drip strip with a little bit extra logic, and still we are able to get performance which matches the performance of Mockingjay. I'm not just shitting on Mockingjay just for fun. Mockingjay is a great policy. It's just that we find it's kind of difficult to implement. Now let's also look at some sensitivity studies, because I just talked about instruction-heavy workloads. So in this sensitivity study, we are looking at data-heavy workloads, which in particular, we are looking at gap workloads. And in this, we can see that these are the performance of the baseline policies that we are comparing against. So SRIP, SHIP, and Mockingjay. Again, everything is related to LRU. If we were to train the IPVs on instruction-heavy workloads, the CVV workloads, this is the performance that we get. And if we were to train the IPVs on data-heavy workloads, that are the gap workloads, we get this performance. So we can see that although we are not able to match the performance of Mockingjay, we can still outperform SHIP and SRIP. And if we were to and if we could retrain on data-heavy workloads, we can again then match performance of Mockingjay. So in conclusion, we find that RRPVs as opposed to LRU positions can be used to generate IPVs. And considering prefetches into our policy actually helps to improve performance. Furthermore, based on these two findings, we invent PackIP, which is a simple and understandable policy which doesn't depend on the program counter and is prefetch aware. In the results, we saw that PackIPV is competitive with other state-of-the-art policies and has manageable hardware overheads. And in summary, it gives 3.3% performance improvement over LRU. Yeah, that's it. If you have any questions, I'm happy to take them.